Okay, I guess we'll be starting. I suppose apparently the Zoom people should be able to hear me because I'm speaking to the microphone here. So welcome everyone to the second seminar of this semester of Applied and Computational Maths seminar series. It is my pleasure to introduce Julian Braun as today's speaker. So Julian and we work together. So Julian is currently a postdoc with Christoph Ortner, who was my PhD advisor.
Oh, it's speaking, but I'm just
Harry O'Quart as a lecturer quite soon.
It's not convenient.
And Julian did his PhD with Bernd Schmidt at Augsburg. That's correct.
Sorry?
Yeah, and we are collaborators, and it's my privilege to introduce it to you all.
Yeah,
and it's over to
okay,
you.
say
Yeah,
4 o'clock.
Julian has a microphone here as well, so hopefully the Zoom people. Let me know if it doesn't work.
Yes, around that. Yes. Okay.
Thank you very much for the
Yeah.
invitation, and thank you for the
Yes.
invitation.
Okay.
To get things rolling
Yes.
in person again, as much as possible. Okay, so today I'll be talking about a joint project with Tom Hudson, who's in Warwick, and Christoph Ortner, who is, well, still my supervisor, but no longer in Warwick. He's in Canada at UBC. And so we've been talking about crystalline defects, and more precisely, the elastic far field and the asymptotic expansion of the elastic far field of crystalline defects. So let's talk a bit about models first, before we can really get into mathematics. And well, most of the talk about models and about analysis, and then at the end I will talk a bit about numerics. For numerics I'm done yet, so I have to excuse if there are any full numerics within it. There won't be too many numerics in this talk. So let's talk with the model for elastic behavior of crystalline material. So let's start with something simple. One can go more general, but let's go with a simple lattice, just a distortion of z to the d, so it's typically 2 or 3d, depending on what you're looking at exactly. So for example, something like this, extended north direction. But I should stop showing this since Brexit is an effect and everything, but since we go outside. So that's the basic lattice, but then of course the precise physical state is not the pure lattice, but there's all kinds of distortions. So what we're really looking at is some displacement of that lattice. So the actual position, right, so the pointer is not really useful on this screen, suppose. The actual position is something like x plus u of x, and so the lattice is really a reference, and then on top of the reference I have some displacement. And so the physics are then covered by classically by potential. So we could go and talk about all kinds of modern quantum mechanical models. But actually, you can fit a lot, even quantum mechanical models, into a kind of a multi-body side potential formulation that I will show you now. So locally, we look at all the displacements in the neighborhood of all kinds of atoms that are close to each other. And we look at the differences of all these displacements, because everything is translation invariant, so you only need to look at differences. And you put them all into a big matrix, which I call du, which is the discrete difference stencil, and that you put into some side potential B, which can be very complicated and can fit to all kinds of different specific energies that you might think, depending on the material and the kind of model. And so then you sum that over all lattice points, and that gives you an energy. And so it's the energy we're looking at. And so physically, what you're looking at is minimizers of energy, or in general, critical points. And there's some mathematical tricks to it. So it's an infinite sum, so you have to be careful that it's actually well defined. But you can do all that. And so basically, as long as b of 0 is 0, a bit of normalization gives you some really nice energy spaces. so some discrete equivalents of H1 and things like that. So you have some energy spaces that you can do some nice analysis. Now, before we get to defects or anything like that, the top is okay. The top is a bit cut off, but that's okay. I can always read what's written there. Let's talk about such a lattice and some properties of such lattice models. The first one being lattice stability. It's
somehow, yeah.
And so the first one is lattice stability, which is a concept that has really been fully developed in all kinds of details only like over the last decade. Before that, all kinds of ad hoc definitions have been used, which weren't always particularly useful. And so this really, but now we have really developed a precise understanding, and quite a few authors, probably more than a list here, were involved in that. Those are the main ones. And so a very simple definition is, okay, you take the Hessian, so the second variation of the energy at zero means at lattice. You take that on let's say a cube of side length n, and you take all the displacements which are zero outside of that, so you have perfect equivalence outside of that, and you minimize this graphic energy compared to H1 type mode. And then, well, you take some limits, and so you kind of go to the full lattice again by taking the limit outside and so on. This gives you a very nice stability constant. And so the first thing to note is, well, if this is negative, then you really have specific nodes for instability, right? So then, in that sense, it's a sharp stability criterion. Now, of course, there are cases where it's in zero and you have some higher order behavior or something, but generally it's a sharp linear stability criterion. So in that sense, it's very nice, but you can do, but it's better than that because this is just one definition. You can do a lot of analysis around this, and there are alternative ways to formulate it, for example, in Fourier space, which are very nice. You can do all kinds of nice analysis and numerics about this. For example, it's very powerful for atomistic continuum results because you can, if you have a Fourier formulation, you can directly identify the continuum by doing the long wave increment. And you can do this for this quantity very nicely. And so there are some papers already that use this very strongly. You can use it to adapt all kinds of PDE techniques because basically it gives you something like ellipticity of the problem. It allows you to really treat even the full nonlinear problem as a elliptic quasi-linear problem. And you cannot directly use PDE techniques, but you can transfer many ideas over. As long as you have this concept of stability, which is the concept of ellipticity. And so, for example, what I did already was discrete Warwick inequality, which is great for that tiny inequality. And one thing it also gives you is that it implies the existence of a lattice Green's function, so a fundamental solution of the discrete linearized problem. And so this is a very important tool that's kind of in the background that has been developed now over a few years. And another general background topic I should mention before I go into the main topic is that, of course, there are continuum models for these kind of problems, which will go by ages. And there's a direct relationship to this discrete model. So each of these discrete models has the corresponding continuum model. You just get the continuum energy density by taking by looking at the discrete energy of affine information per unit volume, which is what this definition says. And then you get your classical continuum theory with continuum elasticity constants if you linearize again. And what you notice, for example, what is a nice property of the lattice stability is that lattice stability implies stability of the continuum problem, of the linearized continuum problem. So the Legendre-Hadamard constant is always bigger or equal than the atomistic one. So of course, the atomistic stability criterion is stronger because you could have instabilities on the atomistic scale, not just the continuums. And And then, of course, you also have Green's function, which is kind of classical for the continuum problem, which I will be referencing. So anyway, this continuum theory is very classical. A lot of the discrete theory is a lot newer. And let's directly go into the first statement about that. Nothing to do with defects yet. Just about this Green's function. So that's what happens if I have a force of the delta or a response to the lattice in the linear setting. That's what the Green's function tells you. And so we have a very good understanding at this point of the lattice Green's function. So there's actually a very nice theorem that gives you everything you need to know about this. So you might think it's very complicated, but if you go into the far field, if you go away from, let's say, what happens between neighboring atoms or atoms that are 3 distance apart, but what happens between atoms that are very far apart, then you can say everything to very high accuracy with continuum theories. And so the full theorem says something like this. The lattice Green's function script G can be approximated by a series of continuum kernels, which are all homogeneous. And the leading order is the continuum Green's function. And the more you take, the higher the accuracy. The accuracy is always measured by decay in the far field. So this doesn't say anything about accuracy about the distance of 5 atoms, but once you go to large distance, this is arbitrary high accuracy just through continuum. And not only are these infinity and unique and all kinds of things like that, they're also easily computable. So, for example, in 3D, we have a nice Fourier formulation which can be reduced to a one-dimensional integral. So it's just an integral over a circle in Fourier space for 3D. Any one of these 3D kernels. This is well known for the continuum Green's function, but we are able to extend that also to the corrector kernels, to the higher order kernels, which gives you the ability to really approximate this Green's function to arbitrary high order. So this is kind of some of the general background, and now I want to come to defects in particular. Unless I want to say something about the proof. I guess we have the time. Just a rough sketch. I want to give you some sketches of some proofs, just to give you the ideas what kind of tools you need, or how elementary or difficult some of these are. How do you tackle something like this? Well, it's all much easier in Fourier space. Okay, so in Fourier space, all you need to do is take an inverse to solve linear elliptically, right? So this is much easier in Fourier space. You take the Hessian, you put it to Fourier space, you Taylor expand, and the Taylor expansion, it means, well, k close to 0 means you're looking at long distances in real space, right? Very high wavelength, this is a long wavelength limit, and so as the highest order in the Taylor expansion, you find the continuum theory. And so the Green's function is always just the inverse in Fourier space. So if you want an inverse of the entire, if you take an inverse of the entire Taylor series, which again is some kind of series of it's matrix valued, so it's going to be not a Taylor series itself. It's going to be, but it's still going to be a series of homogeneous terms, terms with some homogeneity, and Fourier transforms of homogeneous symbols are homogeneous. With some restrictions, so in 2D you might get a logarithm, but this is fully understood what you get. This is called essentially homogeneous. Right, so 2D Laplacian is a logarithm. Clearly they do it, yeah. But that's the general idea. So it's in a way these are fairly basic methods, and some simplified versions of this has been done before. Now let's actually come to defects. So far we've just talked about lattices and Green's functions. So we're going to target all kinds of crystal defects. So we might have a point defect, we might have a dislocation, crack opening, so point defect might be an extra atom or an atom of a different type included, maybe an atom is missing. Could be three combinations of these. This can be all kinds of things. The dislocation means that it's a line defect, so we have this black line there in the middle. If you go around it once, you come out one layer higher. So there would be a screw dislocation. And then other options are, for example, crack opening, which will not be part of our theorems, but it's also one of the cases we are very much looking at, and that I know much. It's very interesting. So I will be mostly focusing on the first two pictures. And then what are your quantities of interest? So you want to know energies, you want to know energy barriers, you want to know the precise core structure around the defect, because it can be very non-trivial, because the potentials can be very complex. You want to know things like transition rates, and yeah, all kinds of quantities like that. And so if you saw my energy earlier, that didn't really look like anything to do with defects. In reality, you have to adapt this a bit depending on what defect you're looking at. So if an atom is missing, then it shouldn't appear in your sum. And then of course, if it's missing, then the potentials of all the atoms around it should look a bit different, and so on. So you need to adapt stuff a bit, but I will not be that notation going further, because that was part of this talk. So I've been kind of ignoring that, but to really include a defect, you have to adapt the energy. And then what you're really looking at is a critical point. So usually a local minimizer, if you're talking about stuff like transition rates, then you might also want to look at the saddle point, which is something we've done in a separate work. And then, okay, in the defect core, so I would always say it's somewhere close to 0. So for an absolute value relatively small, it's impossible to describe the solution analytically, right? The potential is very general. It's multi-body potential, which can have 100 atoms interacting in a complex way. You can't solve the full nonlinear problem close to the defect core analytically. But what you can do is you can try to understand it in the far field. Because in the far field, the solution will look closer and closer to the homogeneous lattice. And the difference to that then can be described by linearizations and new limits and so on. At least we hope. And for the defect core, then what you need, I mean, you still want the defect core, because otherwise you can't say anything about the overall energy or the overall transition rates or anything like that. So what you need there is a good numerical algorithm. And our approach to that is to use the good understanding of the far field as high accuracy boundary conditions. For the core computation, which gives you very fast convergence rates, and means you only have to look at a very small number of degree of freedoms to actually do the core computation. Never get to that in a bit more detail. So what's already known for a few years, well, known to physicists for much longer, but as an actual mathematically precise result, only for a few years, is what the highest order is for dislocations. So, I mean, from a physicist's point of view, this is kind of classical, but we have mathematically rigorous results for that. So for a dislocation, the highest order in the far field for the solution is given by continuum linear elasticity, CRV. And so you should think of an estimate like this, that both du bar and du CLE are at -1, and the error is at -2. So it's a relative error of 1 order there, at -1 there. And you can actually ignore the logarithms. They are important, but not that important. Really about the orders. Right, so this is the leading order behavior of the bar in the far field. So if you use that as boundary condition, that's already not bad for any numerical algorithm, but we hope we can do much better. And okay, so this is just a solution that solves the continuum linear problem equal to 0, and then it's not trivial because you have some boundary condition that makes it really a dislocation problem. And out of focus. So here's a warning for people that like nonlinear elasticity theory, because I know there are always some, including myself, that very much like here's nonlinear elasticity theory. So the problem is, so normally you would expect, okay, linear elasticity gives you one order of accuracy, let's just nonlinear, maybe get more. But that's not the case. So if you just replace it by the nonlinear solution, what I just showed you, you get the exact same estimate. You do not get any improvement, which is a bit surprising maybe at first, because normally that always helps. And I mean, so this doesn't help directly, but what I'm saying is it doesn't help if you just do that. Non-linear terms still play an important role if you want high accuracy, but there's more going on. Okay. So you have to be careful there, which we weren't initially, to be honest. But by now we've figured it all out, luckily. And so a very instructive look is to look at point effects, because for point effects, both linear elasticity theory and non-linear elasticity theory both give you nothing. They tell you this solution should be 0. And if you look at physics literature, they will tell you, okay, the highest order, the leading order, is actually a gradient of a Green's function times some constants. And those constants are called the elastic dipole tensor. And so usually, if you read this in physics literature, it will all be formulated in terms of continuum theories. Because they're not, they don't really do these fully atomistic models for this. But if you want to do higher orders, you need to do atomistic models. You will not get any accuracy with continuum. And so we actually have a rigorous statement of this. So we can prove it. So both du bar and du dipole are A to the minus d. And I'm always looking at the strain, so at du. But you can also prove estimates for the u's themselves, or for the second discrete derivatives, or something like that. You can do all of them, but the strains, so du bar and du dipole, are the most interesting ones. So they are both A to the minus d, and so the error we can prove is 1 order higher, A to the minus d is 1. And we can actually show you can take the different things. Either you do what's known in physics, you take tensor times the gradient of GCLE, so the continuum linear elasticity Green's function gradient times some constants. And these are all tensors, right? I'm like not writing out the whole tensor notations, but it's like a matrix times a free tensor, or something like that. Yeah, exactly that. And alternatively, you can also take the lattice Green's function and then times the different vector, and you can take the discrete differences each, the gradient of course. And why do both work? Well, because what I showed you earlier about lattice Green's functions in the highest order are approximated by the continuum linear elasticity Green's function. And so why is it important that we can take the lattice Green's function as well? Well, because if you want to extend this to a higher order, the continuum Green's function is not going to work. You will have to use the lattice Green's function. Okay, so that's the goal, to really do this to arbitrary high order for both dislocations and point effects. And so that means we want to have not just the first approximation, but one way to write it is successive better approximations as a sum, u0 plus u1 plus and so on plus un, and then hope that we get a rate like a to the minus n. Right? For each term we add one better rate. Here, that is the goal. And so what our conservation so far should tell us that there are two very different contributions. One comes from kind of continuum PDEs. So let's call that UC, and one come from what I call multiple expansion. The first of which we just saw is a constant times the derivative of Green's function. And so in general, these multiple terms are just some tensors times a derivative of Green's function. And so I guess I should directly write script G here, because we want to then take the lattice Green's function for that. Otherwise, it's not going to work for arbitrary. And the continuum terms will solve corrected PDEs. And they resolve a lot of interesting stuff. So they start with linear elasticity, then they resolve nonlinear elasticity. And if you go higher, then they will also resolve strain gradient theory, which is kind of the highest order approximation of the AC error, the atomic continuum error, and even higher derivative theories. And they all come in naturally. However, all these complicated theories will only enter through the right-hand side of this equation. The left-hand side is always going to be the same simple PDE. It's always going to be just the continuum linear elasticity equation. So it's always the second order constant coefficient elastic system, elliptic system, but with some non-trivial right-hand side. And that is sufficient to resolve all these higher order theories sufficiently. Pretty nice. And okay, so this is the general structure. And so let's put that into a theorem. So if we take the first n terms of this of these correctors, then indeed we get an approximation which is accurate up to an error of a to the minus n minus. And so a to the minus n is really the key point. So d was the dimension in which we're working in, but the minus n is the key point. For each term that I add, I gain on it. Okay, and there's some logarithms and which you can't ignore, like they actually do appear, but are kind of not that important as the rate is. And okay, so the multiple terms and the UIs are the multiple terms and the continuum correctors that come from D. And maybe I should say a bit about how these corrector problems really look like. So there are forces on the right-hand side, and how can this be describing nonlinear elasticity or something like that? Where the forces depend potentially nonlinear and potentially through higher derivatives on the lower order terms. So if you obtain all these terms in order, you always only have to solve this linear problem, but you then have higher derivatives of these terms on the right-hand side, and quadratic terms and cubic terms and so on. So how does it look like? Let's write down the first few terms. So there's a way to get all of them, but let's just write the first few down. So WCB, that was the Cauchy-Born energy density, that is the continuum, nonlinear continuum density. So if you take the second derivative at 0, you get your linear elastic constants. And so the third derivative at 0 times the quadratic term, that's the first nonlinearity that appears. So the correct equation for U1 is plugging in U0 into the first nonlinear term and using that as the right-hand side for the corrector. And naturally, if you put in U0 and U1, then that's already a term that's one of the highest, so that goes into U2. Or putting U0 into the cubic terms, also on that order. And then, but then there are other terms. So continuum theory will, continuum nonlinear elasticity theory will only get you that far. So that's why I at least went to U2, where the first completely different term appears, and this is strain gradient term. So the first one that appears here is linear strain gradient theory, which means it's a fourth derivative. So it's a linear term just depending on the fourth derivative. There's also a divergence form and so on. But yes.
The multiple term, they're completely separate.
Yeah.
So you first compute UIC, and then completely separate.
Yes.
And no information from UIC.
So in the theorem, they're completely separate, right? Yeah. Once you get to computation, so the way we're working it at the moment is that the so first of all, they're not independent. So even in the theorem, let's start with the theorem. So why are they not independent? Because here on the right-hand side, you have the full U0 and the full U1, and not just the U1C. So the lower order multiple terms also enter here on the right-hand side. And why is that okay? If this is our continuum P, is well because we can always replace the lattice Green's function with continuum kernels. And certainly we have the infinity function which we can do. Right? So this is how they directly interact with each other. And then, I mean, then how you do computationally, maybe that's another question. But maybe that already answers your question. On the right hand side, there's no C, and that's on purpose. That's not a mistake.
Yeah, but I mean, UIC depends on previous UI. And UIMP does not depend on UIC.
It doesn't.
That's
So, okay, computationally, how we do it at the moment is that we compute them order by order, and we first compute, let's say, U2C, and then we compute U2MP. And then we go to the next order, and that works. So they do interact, but in a way, the interaction is briefly because it only enters in the higher orders. So on each order, you can check it. So another interesting case to look at is going back to point effects. So I already mentioned that case a bit because the leading order is a multiple term, and we can actually do a much stronger result now. So what's interesting is that in this formulation that I gave, in this general formulation, that is that starts with U0. Actually, for a point effect, U0 doesn't exist. It's 0, because if you apply continuum linear theory, it doesn't give you anything. But that means that all kinds of corrector equations are actually trivial, right? They only use 0 enters on the right hand side in every term. So the first 3 continuum correctors are 0, even after U0. And that means that actually the first one that's non-trivial is U4C. And that means before that, you only have the multiple terms. And so you get a much simpler theorem. Just if you cut it off there, after that you get the full theorem of complexity. But if you just go for 3 orders of accuracy, you get just the 3-order multiple expansion and an 8 to the minus 6 error. So the terms themselves are 8 to the minus 3. U bar is 8 to the minus 3. And you can resolve it up to an 8 to the minus 6 error just with the first 3 terms of the list. This is a very nice result. And okay, I would definitely not have I don't think it would be useful to go into the sketch of the proof for that because it's very sketchy and still very complicated. But I want to say a bit about the computations. So this is a very general structure result, but one of our key motivations is to really use this for computational purposes. And so a very straightforward scheme that you can now write down is that you just fix a ball of radius r. Inside of the radius, you let your atoms relax freely, and outside you now fix them to the boundary condition given by this higher order approximation. And now, okay, there's a slight caveat, namely that actually these tensors, these tensors in multiple expansion depend on the defect form. So one way to write it down at first is you say, okay, let's just leave them as degrees of freedom as well. Okay, so this is what I wrote down here. So the degrees of freedom are all the atom positions in the interior, as well as the tensors in the multiple expansion. And if you do that, we have a nice numerical analysis theorem. You can, if you minimize, so the UR bar is the minimizer of this restricted problem, and then you get a converted straight of r to the minus t half minus n minus 1. The key point again being the minus n. So for each order of improvement you put in, you get 1 order better convergence rate. And the energies always behave correctly compared to the H2 norm of this. This is kind of an H1 norm, so given the stability. Okay. And this is still somewhat theoretical result because if you just leave the tensors in the multiple expansion as arbitrary constants, you kind of need to look at the global energy to actually minimize, which is of course not practical. So there's the you need to do something extra. And one way is to not actually leave them as variables, but to compute them beforehand. And we actually have a way to do that, but that's all kind of work in progress. So the full implementation needs a few more things to really make all this work. You need a PDE solver for the UICs, would be the first thing. As I said, this is just a straightforward constant coefficient second order linear-elliptic PDE. However, it's kind of a far field problem, and it's not quite an exterior problem either. It's kind of an underdetermined exterior problem. Because you don't actually have boundary conditions. You need a way to compute the lattice Green's function. For that, it's key what I showed you at the beginning, that you can develop it to continuum kernels. And if you only want 3 orders of accuracy, then you only need to take the first 2 terms in that expansion. And there's a nice Fourier formula for each of these, which is just a one-dimensional integral in Fourier space. The integral of the circuit in Fourier space. So we know a way to do that as well. And the last part is a separate way to compute multiple terms, or some other way to remove the need of actually looking at the global energy. And so we actually have a way for that as well, which is kind of an iterative scheme, but with a small number of iterations. And yeah, but this is still work in progress, so I can't. It's not even at the point where I can really show you much about it. However, since I still want to show you a bit of these numerics, one thing I can do is I can go back a few years, because we started out on this whole thing by looking at some simplified problems, and for those we did numerics, and one of these actually Maciek was involved, so let's just show that one. So this was kind of a screw dislocation case. So if you the most obvious boundary conditions is to take the solution from continuum linearity theory. And what you get there is something that converges like the radius is -1 if you look at larger and larger domains. Right, so the axis here is the radius. And this is, so there's some simplifying assumptions because this was just a test case back then. This is kind of an anti-plane setting and so on. None of that is now needed in our theorem. Our theorem is really generic. And so what happens if you do an improvement? Well, that looks a lot better. Not just such -2, but also it's already for small radii a much smaller error. And so this is the term that you get from adding U1. Adding U1 to your boundary condition. One improvement, you directly get 1 order better convergence rate, as the theorem just told you. And if you add another term, you get another better rate. And then maybe doesn't behave that well for small radii, but you still get the better rate. And yeah, so currently, one of the main things we're working on is really implement the general case. So in 3D with the solver and the 3D Green's function and so on, which is a very nice project. And then hopefully we have more general pictures like this. But yeah, I think it should come to an end soon. A few minutes left. So overall, what this gives us, what we are providing here is a powerful structural result. And I think there are many possible applications for analysis in numeric simplicity defects because it really gives you a lot of details on how these solutions behave. And I think we're just scratching the surface of what can be done with that. But the one application that we directly had in mind are these numerical multi-scale algorithms. Because we can really get high order convergence just by adding a few terms. So by multiplying the computational cost by 3, we get the 3 times higher, 3 orders extra convergence rate or something like that, right? That's pretty crazy. And so one interesting part is that we actually expect the main ideas, the main principles that of this entire theory of using the lattice Green's functions, using these expansions, that these would really work well beyond the scope of our theorem, right? So our theorem is mathematically precise, rigorous. We have to make some restrictions to make that work, which are they only work for dislocation and point effects at the moment, so screw dislocation and point effects. But we really expect this to work more generally. So if you just want to do numerics, for example, even if you're using BFT and not set potentials like I wrote down, or if you want to do a crack opening, by the way, you should be a bit more careful. But that's another topic. But the main principles should still apply. This could be expected in many cases beyond what our precise theory tells us. And so there's a bit of bonus output in all of this. So we now have a really good understanding of the dead space functions, which was just needed for the proofs here, really. That's one of the main reasons we started it, but it's also really nice for the numerics of dead space functions, which is something several people looked in the last decade at least. So we got a really nice theorem there out. And another bonus output is that we actually have now mathematically precise understanding of what the defect diagonal tensor is, which is really one of the most important physical quantities, and probably the most important physical quantity in defect in point defect physics. And we have higher order counterparts as well. And well, once you have a precise mathematical definition and a framework to work in, you can then think about different ways to compute it and what kinds of. And yeah, so as you can imagine, it's not the shortest paper overall, but there you can look it all up. And that's all for your attention.